2 exponent x. So far so good. Now, in case it was not clear how to do numerical derivative, let me show you one more time. Numerical derivative is math, do it with me, and 8. It's like you can just press 8. It's a hotkey, but I wanted to show you this means this. Okay, this machine can graph the derivative. Okay, so math 8. Then this shows up. Then you put x here. And then you put your y1, and this is how, let me remind you how you get to y1. Alpha is a very useful button. Alpha and trace. There's the y1. You get it? I know you can get into the same thing by doing variable, y variable, but this is faster. It's a hotkey. Scroll right, and there you put x. Y'all with me? Okay, and then let's look at the window setting. Although 10 by 10 works, but this is an exponential function, and this worked out nicely during second and third period. X from -3 to 5, and y from -1, because it's all positive, and then 20. Okay, ready? Hit graph. Now, here comes 2 to the x as we know it. Exponential function. Here comes the derivative of 2 to the x. Wait for it. There it is. Do you see it? There she comes. Right there. Right there. Right. Okay. Oh, it's so slow. I know it's calculating the slope at each point. You get it? Wow. Okay. Now we get some information out of the derivative of exponential function, because the power rule here does not work. One thing we learn about this is derivative of exponential function 2 to the x is also exponential function. Do you see that? Further, that base of this exponential function is more like 1.6 or 1.7 to the x, because you know that bigger base meaning steeper curve and smaller base means shallower curve, right? So it's like not quite 2 because it's underneath. So it's like 1.6, 1.7-ish. How about that? Okay, then let's look at this problem. Now we do exactly same activity with 3 to the x. The way that this setup is beautiful is all you have to do is just change that base. And this is a derivative of that y1. You get it? Hit graph button. Boom. So here comes 3 to the x, and here comes the derivative. Oh, it's so slow, right? Do you see it right there, right there, right there? Wow, it's really, really close, right? Those of you who have TI-84 color, you can see 2 different colors. One is blue and the other is red, right? So it's better, easier to see. But it was slightly steeper. So derivative of 3 to the x is maybe like 3.1 to the x, isn't it? It's very, very close. Now, then, of course, it comes to the natural observation. Say there has to be a number between 2 and a 3, and a lot closer to 3 than 2, where the derivative is exactly the same as the function itself. How about that? And this problem says, let's try 2.7, right? So let's try 2.7, shall we? So change that base to 2.7 and do repeat the same thing. Okay, here we go. Boom. So here is 2.7 to the x, and here comes the derivative of 2.7 to, do you see it? No, you don't. Why can't we see it? And those of you with the color, you can see it, right? So why can't you see it on this black and white calculator? Because these curves are on top of each other, get it? They are exactly identical. Oh, well, actually there is slightly off. This was slightly underneath. Can you take a wild guess what this nice number is supposed to be?
E?
Is it E?
E, of course, right? 2.72. Let's try that, shall we? So here's E. Now, since they will be exactly on top of each other, and this is what prompted that study date thing. Okay, in case you don't have color calculator, this is how you can impress your study date. And then, of course, what is a study date? Well, it's kind of similar to study group with a different purpose, different objective, if you will. And that later at the end, if we have time remaining. Okay, so if you can change the type of curve, right? And this upper triangle works pretty well, in my experience, in impressing study date. And you go below here and we keep clicking until you get to this lower triangle. Okay, are you ready to be impressed? Here we go. Wow, look at that. Isn't that spectacular? Oh, the other one is even better. Wait for it. Here she comes. So slow, right? One shades above and the other shades below. How about that? So showing that they are exact fit. They are identical graphs. Okay, if you're doing this alone, you'll never do this. This is a waste of time. But in case you're in a study date, I know to be explained later, then this accomplishes a lot of things. Alrighty? Questions so far? Okay, then let's start this session. So what we have, this is more of a definition, okay? Different mathematicians came up with a different definition of E, but for us, E is the base of an exponential function whose derivative is exactly the same function. You get it? 2.72. Right, how about that? So this is a definition thing. Okay, now, and you can just use that as a fact because it's a definition. But, oh wait, before we go to but part, let's do a little bit of practice. So what would be the derivative? Let's review chain rule. That. And as opposed to derivative of that. Okay, it's an outside function, inside function thing. So this one, outside function is e to the something, isn't it? So you get e to the something. And the chain rule is the derivative of that inside function, which is sine x, right? So that gives you derivative of sine x, cosine x. With me so far? Okay then. What about this one? Now here, outside function is sine something. So derivative of sine something is cosine something, isn't it? And that something is e to the x. And now the derivative of that inside function, which is e to the x, and that is still e to the x. You see how this thing works out? Capish? Okay, that's one nice definition of what E is. But different mathematician has come up with different definition of what E is without talking to each other. These are developed by two different mathematicians. And that is this. Let's say we have function 1 over x, which of course looks like this, right? This computer is really laggy today. And let's say we want to start this thing from 1. So that line is 1 right there. And say we want to go up to what, 5? If we have to calculate this area, and later in this class you will learn how to calculate that curvy area. That area right there is ln 5. You get it? Log base E 5. So if we make a function out of it, so instead of 5, let's say that is just x. This computer really erase. Huh. Now it erases, right? It's really laggy. If that were x, then still waiting for the computer. This is ln x. That is the other definition of what E is. Base of a logarithmic function, right? So whose area is like area under 1 over x from 1 to x happens to be log base EX. And then, of course, there's a proof saying these two are the same number. There's no reason for these two to be the same number. It's one of those things in math. Two different mathematicians independently came up with this, and then they compare their answers, and they are the same. And as if that's not amazing enough, there's yet another mathematician who came up with this exactly same number and totally unrelated area. You can kind of see why these two are related because they're inverse functions of each other, right? ln and e to the x. Yeah, that one. And later you will see why they are more related, but even more unrelated area. Do you remember compound interest formula? Compound interest formula was like this. Your compound interest is principal times 1 plus r. Oh, wait. Really? Okay. 1 plus r over n to the nt power. Remember that? Do you remember forgetting that? This somehow became this formula, continuous interest, as n approaching infinity, right? And then unfortunately nobody sat you down and explained why this is the case, right? Yeah. Today's the day. And this is not, unfortunately, this is not in any textbooks, so pay attention. Okay, all we have to do is this. This, really what I wrote is a limit, isn't it? See, bigger n gives you slightly better pay, so we can take a limit to the infinity every second, right? So what we have is limit as n approaching infinity of p to the 1 plus r over n to the nt power. Good. Now here's a little trick. The trick is we let 1 over k to be r over n. Okay, I want this quantity right here to be 1 over k. Okay, and then limit p, so we have 1 plus 1 over k here. So far so good. That's k. You know, it doesn't look like k at the moment, but it's k, trust me. And then n, oh, we need to figure out n, so we cross multiply this. So this is kr. Good. So we have k r t. And now n disappeared from this expression. So instead of n approaching infinity, let's just look at this. R is a fixed interest rate, constant. So as n approaches infinity, k approaches infinity. Good. With me so far? Now, the rule of exponent would tell you that if I conveniently put bracket right there, this is still exactly the same thing now, isn't it? Okay, well then, this whole thing, notice that this limit, k is only inside this red bracket. So limit only affects what's inside this. Everything else is a constant. So this becomes p to the something, whatever that limit is, to the RT power now, isn't it? And we only need to figure out what the something is, right? This something, limit k approaching infinity of 1 plus 1 over k to the k's power. How about that? Okay, unfortunately on chapter 8, you cannot really understand how to evaluate that limit. I'm going to eventually teach you, and that is kind of the proof equating our definition of E. So, but we can do numerical analysis. Okay, so let's do this. Turn it on. On, I said. On. This computer is stubborn today. On. What is going on, right? On. Will you turn on? Oh my God. Okay. Open parenthesis. 1 plus 1 over, oh, how many zeros are there in, let's do trillion to simulate infinity. I mean, it ain't infinity, but it's good enough, right? How many zeros are there in trillion? 12. Okay, that exponent and trillion there, right? Are you ready? Do you recognize this number, 2.72-ish? In case it was not clear before, oh, not that, wrong constant. Really, what am I doing? They're exactly the same number. Huh, how about that? I know this is not exactly a proof. You have to wait until chapter 8, then I can prove this for you, but this is yet another definition of what E is. If my computer unfreezes, I can write it. So there you go. That's how that thingy becomes P e to the RT. And these three different definitions happen to give you exactly the same number, and they are proofs. Okay, one of them, this is not a proof, but you will kind of appreciate and see why they are somewhat related, okay? Then let's find the derivative of this thing, ln x. Okay? Now, we don't know how to do this yet. So whenever you don't know how to evaluate the derivative, what's our tactic? If this inverse trig function has taught you anything, we write it as an inverse relation like this, eh? Say yes. And then we take the implicit derivative on both sides like this. You get it? Yeah, let's do that. So on the left-hand side, we just learned what the derivative of e to the something is, right? It's e to the something. So we have e to the something, and it's equal to, oh, this side is 1. Wow, what am I forgetting? Somebody tell me my mistake. What did I forget?
dy over dx.
Oh yeah, that thing, because that's literally what you're looking for, and if you drop it, then you don't know where to go, right? Whenever this denominator is dx, so whenever you hit that with y, then you create this thingy, and that's what we are looking for. So dy over dx, of course, is 1 over e to dy. But what is 1 over, what's the e to dy? This thingy is x, right? Do you see that's x right there? Yeah. So what we have here is now 1 over x. Huh, how about that? So here's another very important thing that we learned. Derivative of ln x happens to be 1 over x. You see why this is related? These two definitions are related, e to the x, 1 over x thingy. Yeah, you can also memorize this and use it as a fact without proving it each time. Good?
Mr. Kim,
Yes.
I just have a quick question about how do you get e to the derivative of e to the sine x equals to e to the sine x times cosine x?
Okay, let's go back and let's look at that one. E to the sine x, so outside function is a composite function. Outside function is e, isn't it?
Yes.
Exponential function. Inside function is sine x.
Oh, okay, it's like the chain rule.
Yeah, it's a chain rule right there. Get
Okay.
it?
Same thing to the second one, right?
Yeah. Outside function is sine, which becomes cosine. Inside function gives you this.
Wait, is there a parenthesis between after, like, is x to the e power or to the sine power?
This thing?
No,
The
second one, sine of e to the x.
That means this, right?
Okay.
Okay.
Thank
All
you.
right. Okay. Come back to where we are now. And these are the only two you can just memorize it and use it as a fact. Everything else, of course, you have to show me, right? Okay. Shall we take a derivative of some exponential function other than base e? Yeah, let's do that. What about this? Derivative of log, somebody give me a number. Any number will do.
7.
7. How do we do this then, huh? Okay, this one, you did like this. Do you remember change of base formula of log? Oh, there's my mistake again. I should have you catch this. Do you remember this? Okay, then if you think about it, ln7 is a constant, isn't it? And then this is a derivative of ln x. And we just learned what the derivative of ln x is. And so it's 1 over x. How about that? And if you want to make it look prettier, which you don't have to, then you can write it like that. Good. Your book has this as a formula, but you know how I feel about the formulas, right? Don't you dare, it's automatic 0 if you use it. You can skip from, let's say, here to here even, but you have to show me this thing. Okay?
Mr. Kim,
Yes.
you said there were there were only two that we were allowed to memorize. They
Yeah.
were the one that you're showing right now, and what other one?
This one in the box,
Yes.
and this one in the box.
All
That's
right,
it.
thank you.
Everything else, because the first one is a definition. Second one, it took a little bit of work, but hey, that I will allow. Okay, now, well done. What about the exponential function with some other base? Somebody give me another number. 5. Okay, let's find the derivative of that thing. Okay, did you know that you can change the base of exponential functions? Really? Have you ever seen it? Oh, well, maybe there's a first time for everything. Giant E, this is my giant E technique, followed by ln, and then 5 to the x. Now, do you agree that this is exactly the same expression? Not that inverse functions cancel, no functions ever cancel, but this is positive number, so they appear to cancel each other and then give you this 5 to the x back, right? So this is equivalent expression. However, now we're using the rule of exponent, well, rule of logarithm. We can bring that x to the front, eh? Wait, look what we have here. This is e to the something, isn't it? It's similar to that e to the sine x earlier. So derivative of e to the something is e to the something. And the chain rule applies. What's the derivative of that inside function? X times ln 5 being constant. So this is just x becomes 1 and ln 5. How about that? Good so far? Okay, however, what was this e to the x to the ln 5? Where did we get this in the first place? That's this thing, which is 5 to the x now, isn't it? So what we have is 5 to the x ln 5. How about that? Now your book has this as a formula too, but don't you dare, right? No. If you know what's good for you, you are not going to memorize this as a formula. There's another tactic of doing exactly the same thing, and that's this. We can let y equal to 5 to the x, okay? Equivalent technique. This is what's in the book. The giant E technique is not in the book. Okay, I personally like it a lot. And then we can take ln on both sides. So far so good. It's really the same thing. And then ln 5 has become that x come to the front. Do you see that is kind of what this thing is right there? X come to the front. And now we take the implicit derivative on both sides. You get it? Okay, let's see what this becomes. This is 1 over y. What am I forgetting? What am I forgetting?
D
I
over dx.
prime.
dy over dx, right? And then the right hand side, x became 1, and the constant remains. Still with me? So we multiply by y. But let's remind ourselves, what was y? Y is this thing, isn't it? So we have how about that? Exactly same answer. You can do either one, okay? But this itself, the technique itself is very important. And this is known as the logarithmic differentiation. You take ln on both sides, then differentiate. Get it? I mean, not that you needed it here, but there is one very important application of this, and that is right here. What happens if you want to differentiate this? What? That's not an exponential function. Exponential function has the constant base. This ain't constant. This is one of the fastest growing function that I know. Okay? But we are differentiating it as well. So we just take ln on both sides. We use this technique. And then ln y is equal to that x come to the front. Now we take derivative on both sides. You get it? Let me move this thing out of the way slightly, like that. So this side, we have done it, 1 over y, dy over dx now. Right hand side, x becomes 1, and then ln. Whoa, I almost. See, this is the product rule, right? They are both variable. So this is u prime v plus u. And what was the derivative of ln x? We did it today.
1 over x.
1 over x. They cancel, right? So our dy over dx is equal to y times ln x plus 1. But what was y in the first place? That thingy, right? So we have dy over dx is equal to x to the x times ln x plus 1. How about that? I want to take a derivative of this, but I'm not really doing 1 over that thingy and the chain. Oh my God, quotient. Oh, no. That's humanly impossible. So watch this. This is same thing as derivative of ln x plus 1 minus, this thing becomes minus, right? ln x minus 2 to the 1/2 power. Hopefully this is not too much algebra. You can do this in one shot, or at least in 2 lines. Okay then. Now we take a derivative, so we have 1 over x plus 1 minus 1/2 of, 1 over x minus 2. How about that? And once again, common question. Do we have to find the common denominator, add and simplify? If it doesn't get prettier, it ain't simplification. I would leave it right there. If this were multiple choice question and all the choices have common denominators, then you have to match which one is which. But other than that, leave it. This is where it ends. Okay? Questions? Second problem. Oh, yeah, just like our homework problem. This one, I'm going to let y to be that hideous monster, which is, I'm going to rewrite it, x to the 3 over 4 and x squared plus 1 to the 1/2 power over 3x plus 2 to the 5th power. And the reason I do this is to show you the power of logarithm, right? Logarithms expand, so I'm going to take ln y, and this is ln x to the 3 over 4 power. You get it? Logarithm all over the place. And this is ln x squared plus 1 and 1/2, and this becomes minus ln 3x plus 2 to the 5th power. Now, There's no way for you to break this up because of that plus sign messes you up. So this is as much expansion you can do. Good. Now we take implicit derivative on both sides. So this becomes 1 over y and the chain rule dy over dx. And this becomes 3 over 4 times 1 over 4 plus 1/2. And here we go, right? Chain rule. This chain rule, cannot forget, most common mistake. We'll just tack it up here. And minus 5. And you have 3x plus 2. And then that 3. Good. You notice that I always write denominator first when I differentiate logarithm? Yeah, I mean, it's convenient that way instead of tacking on side. Okay, now multiply y, so dy over dx is equal to y, lots of space. You know why I'm leaving that vast amount of space now, right? So let's clean this up a little bit. 2 cancels. And minus 15 over 3x plus 2. And what was y? Y is this hideous monster, right? This one. I'm going to just copy that one. And here, paste it, shrink it, get rid of this y, get rid of that dot. Erase. Did I just make it worse? Okay. And then shove this thing in. Perfect fit. How about that? And this is as pretty as it will ever get. Questions?
The reason why we don't do y equals 15 for the first example, is it because it already has log?
Yeah, If it has log, then you don't want ln. I mean, you could. This is already nice. Log is a very nice thing. Okay, excellent question. Any other question?
In general, like what do you see in a problem that like tells you it's a good idea to take the log of it?
Okay, here's my personal. It's a personal preference, but whenever I see product rule, quotient rule, then I automatically think about it. Question you're asking yourself is it manageable? Which is faster, easier? Generally, something like this is humanly impossible, right? So taking log is faster. Quick quotient rule, I still think about it because I really loved quotient rule, but you can just use quotient rule on that one. Okay, so it's a judgment call. For something hideous, automatically log on both sides. Log complicates things, but this is infinitely better than the 2 pages thing that many students attempt every year. To use the chain rule, product rule, quotient rule, another chain rule combo. If you do such a thing, it's going to take minimum of 2 pages and you're going to get it wrong anyway. This is humanly impossible to do, right? God, no, don't do this, right? Instead, we do this. Let y to be that hideous monster, okay? And that hideous monster is this. Do you agree? Now, why am I introducing y? I'm not creating another variable to it, so I can take ln on both sides. And behold the power of ln. Number 1/5 out here, right? And then, actually, I'm gonna leave a little space. ln x minus 3 to the 4th power, you get it? Plus ln x squared plus 1. Oh, this one is first power. And this one is minus 1 in the denominator. ln 2x plus 5 to the 3rd power. Too much algebra? Andrew? Andrew, do you have a question?
Oh, sorry, I accidentally hit my space bar.
Okay, no problem. Okay, can we do this in one shot? I mean, if you can't, that's okay, take multiple lines, but this is just algebra so far. Property of logarithmic. Then we do implicit differentiation on both sides. So this thing becomes 1 over y. And the chain rule. Remember the chain rule? And the other side becomes 1/5 of 4 times 1 over x minus 3 plus 1 over x squared plus 1, and find my mistake. There's a mistake right there. And there's another mistake right there. Somebody point out my mistakes.
You need to use the chain rule.
Yeah, this inside function, right? Another chain rule applies right there. This is the most common mistake when you differentiate log. So good for you. So you have to differentiate that inside function, and let's just put it right there instead of tagging it here because I already wrote it. And that one too, right? Let's just clean this up a little bit. So dy over dx now is you multiply y, so 1/5 y, lots of space, and you know what's about to happen. 4 over x minus 3 plus 2x over x squared plus 1 minus, let's say, 6 over 2x plus 5, close parenthesis. And then now we have to multiply this, well, substitute this y. What was y? Because we created y, we cannot leave our answer in terms of variable that we created. This hot mess is y. Oh no. Wait, this is a computer, right? I think I can do that then. Copy that. Paste it somewhere out here. Shrink it. Yeah, that's nice and small enough. And I'm gonna erase this guy. And shove that right. Is it? Does it fit? No. Oh no. Hold on. I can still do this. No, not like that. Get more space. I know, there's no limit to the laziness, right? And okay, and not to forget that 1/5 that I had. Let's squeeze it in here. How about that? You get it? And then the most common question here is, do we have to distribute this and simplify? General rule for simplification. When you simplify anything, it needs to get prettier, not uglier. And if you distribute this, it ain't getting prettier. So this is as pretty as it will ever get. Okay, leave it alone. Okay, now 54. We have a positive constant. Okay, and then derivative. Why are they telling you what the derivative of? Okay, we just take a derivative of ln of kx, right? Yeah, let's do it. You guys want A as well, or just B? I think I heard just B, right? Okay, just B. If you want A, now is the time.
Can you also do A?
A.
What? You want A as
Yeah.
well? Yeah. I mean, all you can eat buffet, right? Then why do you eat a little bit when you can eat a lot? Yeah, it's kind of like that. So, derivative of ln kx. Okay, that is number 1 over kx. And then inside the e, right? Derivative of this inside the e, which is k. And then that's 1 over x. Oh, how about that? Okay, b. Derivative of ln kx, like that, is same as using the property of log, which is ln k plus ln x, then a. And then derivative of this is constant, so derivative of constant is 0 plus derivative of this. Same thing. How about that? Okay. 64 now. Ooh, 64. Bunch of families parabolas, right? And then we have this log with of log. And then for any k and c, they need to be perpendicular, right? Do you even believe it? Should we take a look at it? Yeah, because we got a function that does this, okay. If we have, what's it? X, 1/2 x squared, right?
Negative squared.
Huh? Negative x
Negative 1/2 x squared.
negative sign here, and then let's put like any constant too. So we have something like that, right? And I wish I have a memory. And the other one is ln x plus any constant. Okay. So if you graph ln x with any constant, let's say plus 1. Oh, they appear to be perpendicular right there now, don't they? Huh, how does that work? Well, let me bring this down a little bit then. Instead of plus 1, what happens if I do like -6? Will that still work? Are you a believer? Is that perpendicular? My God, that's amazing now, isn't it? So this is what they are trying to get at. Okay, let's do it. So, you notice that I subscript this thing, y1 and y2, in order to differentiate. That's why I prefer function notation f and g, but hey, that's okay. So, dy1 over dx is negative x, and that's it. K dies, right? Okay, and then dy2 over dx, of course, is 1 over x, right? And these are slopes of these each respective curves, right? So let's see, let's multiply these two slopes. This times this gives you, oh, -1, eh? Is that same thing as saying they are opposite and reciprocal? Which your Algebra 1 teacher taught you that they are perpendicular, hey? Therefore, y1 is perpendicular to y2 everywhere. Huh, how about that? Any other question?